Okay, we've got a cliff with an overhanging plank or board or whatever, and we got a guy standing pretty far down that plank. The pivot point happens at the edge. It's going to be the last point of contact if we're starting to pivot over. So that's our pivot point. It happens to be in the middle of this board. Our 50 kilogram guy has a force of gravity 3x over, since they're telling us each one of those planks or sections is an x. So his 50 kilograms is going to give us 500 newtons of force of gravity down at a position of 3x away. And what do we want to know in terms of what's the current angular acceleration? Well, angular acceleration is torque over rotational inertia. The torque from our guy is 500 times 3x because he's 3x over from the pivot point. So if we have a force of 500 newtons times 3x, and we're going to divide it by rotational inertia. They've given us the rotational inertia of 750. So 500 times 3x divided by 750 will calculate our rotational acceleration, our alpha. When you take the 500 times 3 divided by 750, I believe you get 2. The x is still there. So it'd be 2x radians per second square. We've got a mom and 3 kids on a seesaw. We want to find out, let's see, what the mass of mom is. Don't tell mom. Anyway, let's see. She's sitting R away from the pivot. She has a child that is 1/3 R, a child that is 2/3 R, and a child that is R from the pivot. Each child has a mass of M. So on the left side, when we're looking at total, or we're looking at the torques being, we would have 1/3 R times M. I'll call it MR. It's my preference. You can rearrange variables when they're being multiplied. So 1/3 MR plus 2/3 MR plus MR. That's on the left side. If this system's at equilibrium, that means balanced torques, constant velocity, no acceleration, all the good stuff. So the mom's mass, we'll have to call it x because I don't want to overdo any variables. So we're going to solve for x times r because she's r distance from the radius. Easiest thing to do is cancel all the r's. Then I would have 1/3 m plus 2/3 m plus m is equal to x. 1/3 plus 2/3 is 1, plus 1 is 2m, so 2m is x. If mom and kids slide closer to the axis of rotation, what happens to the mom-kid seesaw system moment of inertia? Moment of inertia, in its most basic form, is mr squared. If you take the distribution of the mass and you bring it inwards, you will have a reduced r in that mr square. So you're going to have a reduced rotation of inertia. Total mass stayed the same, but the distribution of the mass changed. So it is going to be reduced. It's going to be smaller. This poor donkey's having to exert a lot of force to pull a circular wheel that grinds on corn. He's located R from the axis of rotation. So I'll draw that in the picture. Just from that center of that disc he's walking around out to him is a distance of R. If the frictional torque between the wheel and the corn is T, or tau, how much force in terms of R does the donkey have to provide in order to maintain a constant tangential velocity? Constant velocity. Well, it would be a constant velocity, right? Well, the tangential velocity, it's changing direction. Let's call it tangential speed. It just makes me feel better. Constant velocity means balanced forces. Balanced forces means equilibrium, balanced torque, all the good stuff. So his force times his distance has to equal the tau that they gave us, the T, the torque. So F times R is equal to T. Divide the R over, and you get F is T over R, or torque over radius. If the donkey was pulling at a 45 degree from the radial line, how much force would he need to generate the same torque? Well, here we're just going to say force times R times the sine of 45 has to equal the torque. And we're just going to divide R and the sine of 45 to the other side. I'm just keeping it simple. So the force is going to be the torque of the corn divided by R times sine of 45. Certainly you could solve for sine of 45. Here I'm just rearranging to show where the information comes from. And that's your solution.